In section 11.4, we're going to talk about something called a logarithmic function. A logarithmic function is an inverse of an exponential function. So we're going to start with the exponential function y equals 5 to the x power. And we're going to graph real quick. So I'll start with 5 to the 0 power, which is 1. 5 to the first power is 5. 1, 2, 3, 4, 5. 5 to the second power is 25, so it's way too high off the graph. 5 to the negative first power is 1 over 5, and 5 to the negative second power is 1 over 25. And as we know with exponential functions, the x-axis is an asymptote. The graph will get continuously closer to the x-axis as it continues to travel to the left along the x-axis, but it won't actually touch or cross. The graph of the inverse, remember an inverse is what you get when you take the ordered pairs and you flip them. So we know that one of the ordered pairs on the graph is negative 1, 1/5. So on the inverse, it'll be 1/5, negative 1, which will be like here. 0, 1 is on the graph. So 1, 0 is on the inverse. 1, 5 is on the graph. So 5, 1 is on the inverse. And then we're going to see that the graph of the inverse is going to look like this. The green graph is called the graph of a log. And the log, and we'll talk about where these numbers come from in a minute, it's going to be log base 5 of x equals y. By definition, to convert between exponential form and log form, we will use this definition at the top of the page. This side is called exponential form. The reason it's called exponential form is because it's a number to a power equals something. This side is called logarithmic form, and we abbreviate the word logarithmic by calling it log. So the way it's pronounced, which is very specific, is log base A of x equals y. The little weird arrow in the between says it means the same thing as a to the y power equals x. The reason this a is called a base is because this a is also called a base. Notice that in log form, what the log is equal to is actually the exponent of that base. So in example 1, we're going to rewrite each of these log forms in exponential form. So if you look at the definition at the top, the log base 27 of 3 equals 1/3, if and only if. So the base is 27. What it's equal to is the exponent. And then the exponential form is going to equal this number here. Now, the expression you get when you're done converting should be mathematically true. 27 to the 1/3 power, which is the same thing as the cube root of 27, is equal to 3. So we must have written this correctly. In part B, log base 16 of 4 is equal to 1/2. In exponential form, the base is 16. The exponent will be 1/2, and that will equal 4. Remember, 16 to the 1/2 power is the same thing as the square root of 16, which does equal 4. What if I want to go the other direction, though? What if I give you something in exponential form and I want to write it in log form? So in example 2, 2 to the 10th power is 1024. So the log base 2 of 1024 will equal 10. Remember, the base of the exponential term is the same as the base of the log. And the log will always equal the exponent. In part B, the log base 2 of 1/8 will equal -3. The reason that we learn to convert between log and exponential form is because the next step will be to take these to application problems where in order to solve them algebraically, it might behoove us to change from log form to exponential form or from exponential form to log form. In example 3, it says evaluate the expression, the log base 5 of 1 over 625. So this is how I normally teach it to Algebra 2 students. I make them set this equal to x. And then I have them rewrite it in exponential form. So in exponential form, it's going to be 5 to the x equals 1 over 625. In order for a number to be raised to a power and result in a fraction, the exponent must be negative. Remember, negative exponents flip the fraction. Well, it can't be 5 to the negative first power because it's 1 over 5. 5 to the negative second power is 1 over 25. 5 to the negative third power is 1 over 125. So if you keep playing with this, you're going to figure out that x is equal to negative 4. And you can just play with it a little bit in your calculator. In a little while, I'll actually show you there is another way of evaluating this on your calculator. But for now, I wanted to do guess and check. Example 4. How many years will it take $700 invested at 12% compounded annually to amount to $47,000? Remember, in our money problems, you have one of two equations to choose from. You can either choose this equation or this equation. I should rephrase that. You don't really get a choice. You have to pick the correct equation for this particular scenario. So how do you know which one to pick? The key is in this phrase. Compounded annually means you have to use the second one, because the first one is only for continuous compounding. So if I'm compounding annually, I know n equals 1. I know the amount that I will equal at the end will be $47,000. I know that the initial investment is $700, and I know that the rate is 12% or 0.12. What I don't know is the time. So let's plug our numbers in. 47,000 is equal to 700, 1 plus 0.12 over 1 raised to the 1 times t. Some of this stuff I can simplify in a minute. We'll deal with that in a second. So in order to solve this problem algebraically, the first thing you should do is get rid of 700 by dividing by 700. So 47,000 divided by 700 is going to give you a decimal. So because I want to get the most exact answer I can get, I'm just going to leave it like this. In the parentheses, 1 plus 0.12 is 1.12, and then 1 times t is just t. This is an exponential equation because the variable is in the exponent. In order to solve this equation, it might help us to convert it to log form. So in log form, it's log base 1.12 of 47,000 over 700 is equal to t. Most of you should have a location on your calculator that will do this problem for you. It's under the math menu, and if you scroll to the bottom, you should see a function called log base. If you don't have that function, I will show you another way of evaluating this in your calculator. But if you have, under the math menu, you scroll down and find log base and you hit enter. What you'll do is you first plug in the base, and in this case it's 1.12, and then you'll arrow to the parentheses and put in the 47,000 divided by 700. Get out of it and then hit enter, and it'll spit out the answer for you. which is approximately 37.1, and it's going to be years because that's the unit of measurement for these particular problems. However, if you don't have this log-based function, I will show you another way, and this will come back up again. We have something called the base change formula. The way the base change formula works is we're going to rewrite this log in a format that we can do in our calculator. The button on the left-hand side of your calculator that says LOG has a special base, and that base is 10. Well, that base does not say 10. So the way it works is the log base A of x can be rewritten as the log of x over the log of A, and then you can just shove it in your calculator. So in our particular problem, it's going to be the log of 47,000 over 700 divided by the log of 1.12. And if you do that in your calculator, you should get the exact same answer that we got by using log base. And I'm testing it just to make sure, and I did get 37.1. The last thing that we're going to talk about are properties of logarithms. In order to solve problems with logarithms, you can't really do anything unless you have a single log on each side of the equal sign, or a single log on one side of the equal sign. If you have more than one log being added or subtracted, we're going to need to rewrite it so that we can evaluate it. The properties of logs were the log base b of m times n is equivalent to the log base b of m plus the log base b of n. The log base b of m divided by n is the same as log base b of m minus log base b of n. The log base b of m raised to the p power can be rewritten as p times the log base b of m. And if two logs are equal to each other, they literally cancel, and you're left with m equals n. So in problem number 5, in order to solve part A, the first thing that I would do is I would take that 1/6 power and I would put it in front of the log. That's the power rule. And then I would get rid of the 1/6 by multiplying the other side by 6. So I would get the log base b of 15,625 is equal to -2. Then I would rewrite this in exponential form. B to the -2nd power is equal to 15,625. We don't like negative exponents, so I could rewrite this as 1 over b squared is equal to 15,625. So b squared must equal 1 over 15,625. And then I would square root both of these. And the nice thing about this problem is you just have to take the square root of the numerator, which is 1, and the square root of the denominator, which is 125. So again, what I did was first I got rid of the exponent by writing it in front of the log. And then I divided by 1/6, which is the same as multiplying by the reciprocal, and -1/3 times 6 is -2. Then I rewrote it in exponential form, and I got b to the -2nd is equal to 15,625. But we don't like negative exponents, so b over -2, or b raised to the -2, is the same as 1 over b squared. And then if I flip 1 over b squared, I have to flip the other side of the equation. So I got b squared is equal to 1 over 15,625, and then I took the square root, and I found out that b was 1 over 125. In part B, I want you to notice that those logs are equal to each other and they have the same base. If they have the same base, then they literally just go away, and you're left with 2x plus 5 is equal to 5x minus 4. So 9 is equal to 3x, or x is equal to 3. In part C, I want you to notice that I have 2 logs being subtracted. In order to simplify this expression, I'm going to rewrite this using one of the properties up here. And the property I'm going to use is the quotient property. When you have 2 logs with the same base being subtracted, you can rewrite them as a division problem. And it's a particular order. The 4x plus 5 has to be in the numerator, and the 3 minus 2x has to be in the denominator. Now I've combined it into a single log. Once I do that, I can rewrite it in exponential form. In exponential form, it's going to be 3 squared is equal to 4x plus 5 over 3 minus 2x. This is just a proportion. 3 squared is 9. And then I'm going to cross multiply. So I'm going to get 27 minus 18x is equal to 4x plus 5. And then I solve for x. I'm going to put my constants on the left and my variables on the right. I should erase this because 27 minus 5 is 22. So I get 22 is equal to 22x. So x is equal to 1. And that was logarithmic functions.